All right, here we're looking at the beginning of Chapter 4, and we're going to start with Section 1. So our learning targets for today, first we're going to identify polynomial functions. And here in this whole unit, we're really getting into polynomials and rational functions. So we're going to look at those polynomial functions and their degree, and then we're going to graph them using our transformations. And we've used these transformations on many other families of functions before, so we're going to use these same transformations. We're going to find the real zeros and their multiplicity. Then we're going to look at some graphs of those polynomial functions. And then we're going to look at some specific polynomials. We're going to look at some cubic models. All right, so the first thing we deal with our polynomial. So our polynomial means many terms. So there's always going to be many, many terms in our polynomial. So when we're writing our polynomial out, to write it in standard form, we always start with the highest exponent and then work our way down till we get to our constant. Okay, so we have our coefficients. So coefficients are the numbers in front of our variables. The leading coefficient is the number that's in front of the variable with the highest exponent, and that exponent tells us the degree of the polynomial. Okay, so when we're looking at the domain of polynomial, we're always going to be looking at all real numbers for our domain. So let's first figure out what we have here. So a couple of polynomial functions. So we want to identify if these are polynomials or not. So the first thing we notice is this one here. I just have some values, some numbers, and then I have some variables with exponents. So yep, that one is a polynomial. Let's look here. Even this one, though this one is written differently, we could rewrite this in the correct form. We could have 3x to the fourth plus x plus 2. So that can also be a polynomial. Here, since I have this square root, this one is not a polynomial. Here I see I have two different polynomials. I have one in the numerator and I have one in the denominator. This is what we call a rational function, and we'll get there in the next section. So that is not a polynomial function. This letter E, even though it's just a single number, can be written as a polynomial. So yep, that one works. And then again here, if I expand this out and distribute, I end up with just some values with some exponents. So yep, that one would be a polynomial as well. So here's exactly what we already talked about. So we also want to look at our leading coefficient. So let's look at part A. So our leading coefficient is the number that is with the highest exponent. So my leading coefficient here would be 5. My constant would be a -9, and my degree would be 3. For that polynomial. So I can look at that and see those pieces of it. Okay. We also have different degrees, and they do different things, and we'll look at several of them. Right? We've looked at some constant functions. This is kind of the graph of the x-axis, right? Or it can be any other number along the x-axis. We look at some constants at those horizontal lines. We've looked at linear functions a lot where I don't have an exponent. My exponent would be 1. My degree is 1. And then we looked at where our degree is 2, and that's a quadratic function. Okay. So when we're dealing with polynomials, we know that a polynomial has to be a smooth continuous function. So here you can see this example is a smooth continuous function. I know it's continuous because I don't have to pick my pen up off the paper when I'm drawing it. And then it also has to be smooth. Here cannot be a polynomial because I have first a corner. A corner tells me it's also not a polynomial. This little piece is called a cusp, not in a polynomial. I have a gap where I would have to actually pick up my pencil, and then I have a hole. So we'll see some of these functions in calculus, but these are not polynomials. Remember that a polynomial has to be smooth and continuous. Okay. So here is our next definition, that a power function of degree n is a monomial function of this form. Okay, so I like these little hints for us. So in like human terms, a power function is defined by a single monomial. So a power function has just one term with it. So let's look at these real quick and what they look like graphically. So when we have these, we can kind of see the difference. We're graphed through the origin of these power functions, and then the larger my exponent gets, the steeper my graph gets. So I still kind of go through the same spot, but you'll see my x to the 4th in blue, and then x to the 8th in red, and then x to the 12th in black. So we just seem to get more steep more quickly the higher the exponent goes. Okay. So here's some properties of these power functions. So if my exponent, right, is even, these are the big things to note. So if the exponent is even, then I know that my f is an even function, so my graph is symmetric with respect to the y-axis. So I can fold it across the y-axis and it'll be the same. So my domain is going to be all real numbers, and the range is going to be all non-negative real numbers. So it's going to be greater than or equal to 0. My graph will always contain the points of the origin, -1, 1, and 1, 1. And then as the exponent increases in magnitude, the graph is steeper, right? So, but closer to the origin, it flattens out. So just what we looked at on that last page. Okay, so now we're going to look at these ones. So this is where I have an odd n value. So these last ones I looked at, I had an even n, so here I have an odd. So we see that it just looks a little bit differently. Okay, so you'll see this black graph is y equals x cubed. The blue graph is y equals x to the n, so with n being greater than 5. Right, so again, just like the last one, the closer we get to the origin, we kind of flatten out, but the further away we get steeper very quickly, the larger our n value gets. And again here, right, I've got my x to the 5th and x to the 9th. So again, the larger the exponent, the more I flatten out near the origin, but I get steeper much faster. Okay, same thing here. Okay, so when we have this odd n, now let's look at these functions, okay? So that tells me that f is going to be an odd function. So it's symmetric with respect to the origin, which looks just like this, right? Because I'm symmetric this way across the origin. Okay? So my domain and my range are all real numbers. If this is my n is odd, I'm still containing this 0, 0, and 1, 1. However, now I have this -1, -1, whereas when this was even, this was a positive 1. So again, as my exponent increases, the graph is steeper the further away it gets, but closer to the origin, it's a lot flatter and closer to my x-axis. Okay? Now let's look at these polynomials and use our transformations. So we're going to use our same transformations, our a, h, and k, to deal with these functions as well. Okay? So here's this first graph. We're going to look at 1 minus x to the 5th. So first I want to start with kind of my parent, which is x to the 5th, which looks like this, right? I know I contain the points 0, 0, 1, 1, and -1, -1, and we can look at the steepness based on this exponent. So then I multiply by a -1. This -1 is going to reflect it about my x-axis, so I do that reflection, and then I add 1, so my entire graph shifts up 1, right? So it's still following our same rules of transformations, and then I can follow these 3 points along the whole time, which is kind of handy. So now here's our next example. We're going to graph this polynomial. So I've got 1/2 times the quantity x minus 1 to the 4th. So let's see what that looks like. So I have the different stages, right? Because I always want to start with the most simple function that I have. Okay. So I've got my x to the 4th is my just standard polynomial here. So again, I contain the point 0, 0, 1, 1, and -1, 1. And it's an even number, so I know that it's going to be symmetric about the y-axis. And so that's what that looks like. Well, so now I replace my x with an x minus 1, which shifts everything 1 unit to the right. So I move all those 3 points. And then I multiply everything by 1/2, and this 1/2 is a vertical shrink, so I know it's going to get a little bit shorter and fatter. So that's how that can work, and that's how that looks too. And we always want to do this step by step. We always start with our parent, and then we kind of do the different transformations to it from there. So now that we've done those transformations, we're going to look at some of the real zeros. And remember, when we deal with quadratics, we could have some imaginary zeros. Really, right now, we're just going to deal with the real zeros. So a real zero is where my function crosses the x-axis. So here you can see I have 4 zeros. Then, once we find the zeros of a polynomial function, we have to determine, well, does it cross the x-axis or does it just touch the x-axis? Because that changes what we're looking at. So here, if we're looking at values, and we'll do this in a little bit when we're plugging in values, you can see whether it's below or above, and that tells you if I cross or if I just touch. And there is kind of a difference when we get to graphing these. Okay, so if f is a function and r is a real number, so when I put r in to my function, if I get 0 out of my function, then r is a real 0. That's one way I can tell if values that I have are zeros of my function. Okay, so one thing to keep in mind is we have many different ways to say a 0. Okay, so I could say a 0, I could say an x-intercept, I could have x minus r being a factor of f, or I can use the word solution. All of these things are the same. So no matter which one of these wordings you hear, we're always looking for where it crosses the x-axis. So here we're going to find a polynomial from its zeros. So I'm going to be given its zeros, kind of its degree, and I have to write the polynomial from that. And then I need to graph it to verify my result. Okay, so the first thing I know is that if r is a real zero, then x minus r is a factor. So I can go ahead and rewrite this. So I know I'm going to have factors of x plus 3, right, because I have x minus r, and that r was a negative 3. So I've got x plus 3, x plus minus 2, and x minus 5. So I know those are all factors. So I know when I'm dealing with factors, I can multiply them all together to get my real function. Here I don't really know what a is, but a could be many different things. So a just tells me the stretch or shrink, right? So how steep it's going to be or how flat it's going to be. It doesn't actually change any of the zeros. So I can kind of pick any a value for that one. So we're going to just decide that a can be 1, right? We're going to be the most simple as we can. So I go ahead and I expand my polynomial. So I multiply out my binomials, and I end up with x cubed minus 4x squared minus 11x plus 30. So then I can go ahead and graph that. And I see that, yes, those are my zeros. I was correct in my equation. And I could choose many different values of a, but when we're writing our equation, generally you want to pick the most simple. So we generally use an a value of 1. Okay. So now here we're going to talk about some multiplicity. Okay, so if x minus r to the m is a factor of my polynomial, and I have this x minus r to the m plus 1 is not a factor, then r is a 0 of multiplicity. So let's actually kind of see what this looks like. Okay, so here's my original polynomial. I've got 5x squared times the quantity x plus 2 times quantity x minus 1/2 to the 4th. So negative 2 is a 0 of multiplicity 1, because my exponent of my factor here, my x plus 2, is 1. Okay, so this would be my r, would be a negative 2, is my 0 of multiplicity 1, because that's my exponent. Okay, 0 is a multiplicity of 2, because the exponent of my 5x squared is 2. And so the exponent here, and my r value right here, right, would be 0, because it's x minus 0 squared. So 1/2, my x minus r, so my r is 1/2, is a 0 of multiplicity 4, because I have that exponent there. So now we're going to graph some polynomials using our x-intercepts. So here's our first polynomial. I've got f of x equals the quantity x plus 1 squared times the quantity x minus 2. So first thing I want to find when I'm graphing this is my x and y intercepts. Then I can use my x-intercepts to find those intervals that I was talking about before. Well, does my x-intercept cross the x-axis, or does it just touch? So I can use that to figure out where I actually cross and where I just touch. And then I find some other points on the graph and then draw them as a curve. So the first thing I want to do is find the y-intercept. So in order to find the y-intercept, I plug in 0 for x, right, which kind of simplifies the entire thing, which gives me a negative 2. So then I want to find my x-intercepts. So to find the x-intercepts, I set y to 0. Well, and this is already kind of factored out for me. So when I set each piece equal to 0, using the 0 product property, so I see that x equals a negative 1 or x equals 2. So those are my two x-intercepts. Okay? So now I have 3 different intervals. I have from negative infinity to negative 1. I have from negative 1 to 2, and then I have 2 to infinity. And I just found those intervals by taking my x-intercepts. And I can have many, many intervals, but those are the ones from this actual function. Okay? So I know that my graph is either going to be above or below in these intervals. So I pick a number in each piece. So I would pick a value that falls below negative 1. I'd pick a value that falls between negative 1 and 2. And I'd pick a value that falls between 2 and infinity, so above 2, and plug that into my function, and let's see what we can see here. Okay, so here's my intervals. So I pick a negative 2 down here just because it's simple. I plug it into my function and I end up with a negative 4. So I see I'm below my x-axis. That also gives me another point that I can graph. I'm going to pick something in between here. And here we pick 1. You could pick 0, you could pick any number that falls in this interval. Well, when I plug 1 in, I get a negative 4, so I know I'm still below my x-axis. Then I'm going to pick a number greater than 2. So here we pick 3, we plug that in, we get 16, so I see I'm above my x-axis. So that tells me the directions that my graph is going to go. Okay, so here we also got these 3 extra points that we could graph as well. Okay, so now we're going to graph all those points. So I graphed my y-intercept, and I graphed my x-intercepts, and I graphed those other points that I found. And I just connect all of those points with my smooth curve. So I do see that here I'm below, I'm still below, and then I'm above my x-axis. So that does match with exactly what I found in the table before. Okay, so if r is a 0 of even multiplicity, right? We talked some multiplicities. So when I have an even multiplicity, my graph touches the x-axis. That's the big thing. We don't cross it. We touch if I have that even multiplicity. So if I have odd multiplicity, that's where I actually cross the x-axis, where I go from either positive to negative or negative to positive. So then we have these other things called turning points. So in this graph, right, you can see I don't only just touch my x-axis. I have right here would be considered a turning point, okay, because I'm still changing direction in my graph. Okay. So sometimes we don't know exactly how low or how high the graph goes between those points. So I know that, but I do know that it changes direction. Okay, so this is where my local maximums and local minimums come into play. And we dealt with these in chapter 2. Okay, so we're going to be using some technology to help us find these turning points. Okay, so if f is a polynomial of degree n, right, and we're always dealing with degree n, then our graph has at most n minus 1 turning points. And we'll actually look at what this looks like in the graph because that helps. Okay, and then on the flip side of that, if the graph has n minus 1 turning points, then the degree is at least n. So let's actually just look at what this looks like. So here I can see I have my x plus 1 squared times x minus 2. We've actually focused in on this on the graph. And we can do this on Desmos as well, because we can see kind of where it is, and then we can use our minimum or maximum function, or in Desmos just click on the point and it'll tell us exactly where it is. So without this, it's really hard to calculate what the minimums or maximums are, so we're going to go ahead and use those graphing things to help us. So here we want to identify the graph of a polynomial. Now remember we said that a polynomial has to be a smooth, continuous curve, so we have to figure out which one of these graphs, if several of them, could be polynomials. We'll see here I have to pick up my pencil in order to get to this through this gap, so I know that this is not going to be a polynomial function. Here I can draw a continuous curve. I don't have any cusps or corners, so yep, that one works. Here on C, I have this drastic change, and that's a corner. It really could be a cusp, either one of those two. But either way, this is not a polynomial function. And then again, I can draw my continuous curve. That one works too. So those are my polynomial functions just based on the graph. Okay. So now we want to look at end behavior of these graphs. So we looked at what happens kind of in the middle, right where I'm touching my x-axis. I figured out how do I find where it touches the x-axis? What does it look like in between those intervals? Now I have to look at the end behavior. What does it look like as I go, as x approaches infinity or negative infinity? That's really what we're looking at. Okay, so here's our theorem. So it tells me that for large values of x, right, and when we're talking large, we're talking as we near infinity, the graph of my polynomial function, right, resembles the graph of the power function. So again, in human terms, the end behavior of a polynomial resembles that of its leading term. So when we're dealing with polynomials, we always first get them in standard form with the highest exponent first. Then that highest exponent is going to help us determine what the end behavior looks like. So let's look at this one. Okay, so we can do this. Here's my function. I have a negative 2x cubed plus 5x squared plus x minus 4. So what I really want to do is I want to test this out to see what the end behavior looks like as x approaches infinity. So in order for us to test what our end behavior is going to look like as we approach infinity, we grab some x values. So we start with a more manageable x value, right? And I plug it in, and I kind of see what I'm looking at into my actual function. And then I continue to increase my x values. And I increase them by quite a bit each time. So I see that as my x value increases, my f of x value greatly increases as well. But it also does show that I am getting very close to what my leading term was, right? And my power function. And that's what we looked at on a couple slides ago, is that our end behavior is going to resemble this leading term. And here we can see that it actually does. So the further away from 0 we get, the closer they resemble. So you'll see here right near 0, it's not that close. But as I continue my graph towards infinity, it will get closer and closer. So here's kind of what our end behavior looks like. And this would be something really good to remember, just so you don't have to graph everything all the time. So if my n value is greater than or equal to 2, and it's even, and then my a sub n is greater than 0, so my leading coefficient is greater than 0, it's positive, my n is greater than or equal to 2 and it's even, my end behavior is going to go up towards the negative and up towards the positive. And here's how we read this. F of x approaches infinity as x approaches infinity. So then you'll notice here I'm still dealing with even, but here my a is negative, so it's going to be going down. Okay, so the big thing is to remember, if I have even here, remember we're dealing with an even function, so it's going to be either both up or down. So now what happens if we're odd? So if a is positive, I start kind of down and I go up. If a is negative, I start up and I go down. Okay, so those are just some kind of things to remember, so you don't actually have to graph every single polynomial you get in order to see the end behavior. Okay, so now let's look at this. So which of these graphs could be x to the fourth plus ax cubed plus bx squared minus 5x minus 6? So I see that a is greater than 0 and b is going to be greater than 0 as well. Okay, so I can look through these, and first I want to determine my end behavior. So I see I have an even, so I know it's going to be an even, which all of these are, but it's positive, so I know it can only be one of these first few. So then I'm going to actually have to sit down and figure out, well, how many times do I cross the axis? Okay, so I know my y-intercept is going to be at -6, so I eliminate this first one because my y-intercept is above the x-axis, so I know that one's gone. And remember, to find the y-intercept, I plug in 0 for all of my x values. Okay, so I'm not really able to solve this one because I don't have numbers, right? So I move on to figure out the turning points. So since f is a degree of 4, my graph has at most 3 turning points. So I can also get rid of, oops, wrong way, this graph, because here I have 5 turning points, right? 1, 2, 3, 4, 5. So that one's not going to work. So I know that much as well. So now I can look at that end behavior. And so, like we said earlier, we knew that this one couldn't work because my leading coefficient is positive, so it has to go up. So this is the only graph that could possibly resemble this function. Okay, so I can look at just simple things like this, and I don't need the numbers in order to get me there. So now we're going to be writing a polynomial function from the graph and what information I'm given. Okay, so I want to use the smallest degree possible. So the first things I look at is I look at all of my intercepts, which I have at -2, 0, 0, 0, and 2, 0, and then I'm given this extra point as well. Okay, so first I start with my x-intercepts. So I know that my factors are going to be x plus 2, x, and x minus 2. So I can rewrite my function, right? So I've got my ax times my x plus 2 squared plus times my x minus 2. Okay, and I know that this is going to have a squared component because I only touch the x-axis here. I never cross through it. And if I touch the x-axis, I have to have an even exponent. So I have to put an exponent with this factor. So that's where this squared comes from. So now all I have to do is find a. So I go ahead and I plug in that other point that I was given, that -1, 6, as my x and my y, and I solve. So my a ends up being 2. Okay. So now my function is 2x times the quantity x plus 2 squared times x minus 2, has that same graph. So then I could just graph it on Desmos or my graphing calculator and double check. So big thing when we're writing these, definitely you have to look at our multiplicity to see where I either touch the x-axis or if I go through it. Right here I go through and here I go through, so I don't have to change the exponents there. But this factor I actually just touched, so I do have to have that even exponent. So now we're going to be looking at some more graphs and analyzing these graphs of polynomials. Okay? So I want to analyze the factored form of the polynomial 2x minus 1 times 2x plus 1 times x plus 3 squared. So again, I want to look at the end behavior of the graphs. So I expand my polynomial. So I multiply everything out and then I combine my like terms. So here's my expanded polynomial. And to look at end behavior, remember we always kind of look at this beginning, this leading term. Okay? Then the next thing I want to look at is finding my x and y intercepts. So my y-intercept, again, is I plug in 0 for x and I find that I have -9. My x-intercepts I can solve. And this is handy because this is already factored for me. So I just set each piece equal to 0 and solve. So my x-intercepts are plus or minus 1/2 and a -3. And then I have my y-intercept of a -9. So now I can figure out their multiplicity. Okay, and we can use that from our actual function. So I can look at where I'm actually going to cross the graph and where I'm actually just going to touch the graph. So my zeros were that's plus or minus 1/2 and -3. So plus or minus 1/2 are a multiplicity of 1. So that means I cross at the x-axis. And I know that they're a multiplicity of 1 because I have no exponent with them right there in my factored form. But my 0 that's at -3 is a 0 of multiplicity 2. So I know I just touch the graph, touch my x-axis at that point. I don't go through it. So now I can figure out the maximum number of turning points on this graph. And so I know I'm going to have at most 3 turning points. So then I can go and graph the pieces that I know. So I know my x-intercepts and I know my y-intercept and I know my end behavior is going to resemble that function. So then I just have to kind of figure out what it's going to look like in between. So I figure out some more points and just plot those and go from there. So then I go ahead and graph that and kind of see what it looks like to see where my turning points are going to be. Okay. We can also just look at our graph and find our points from there as well and kind of analyze it. So we've been dealing with real zeros. So here you'll see I also have this turning point that's not a 0, and that can make it a little more difficult to see. But here again, my end behavior resembles the leading term, and then I can just find other points. So now here's our last learning target. We're going to be building cubic models from data. Okay, so a cubic relation is where I have my degree of 3. So this is kind of what I'm looking like. So when A, right, and we always want to deal with A. When A is positive, I kind of start at the bottom and go up. When A is negative, I kind of start up, I have some turning points, and I go down. Those are the just general looks of that cubic function. Okay, so we can also use Desmos or our graphing calculator to find our cubic regression. Okay, and that's what we're going to be doing here. So the data that we're going to look at in just a second represents the weekly cost of printing X 1,000 textbooks. So draw a scatter diagram of the data as with X as my independent and C as my dependent. So then I have to look at what type of relation that looks like. So then I want to use my graphing utility, and here I would use Desmos to find my line of best fit or my cubic function of best fit. Then we can graph it and then use that function to predict some things. So first of all, here's our table of data, and when we have this table, we'll just go ahead and put it in Desmos. And in our graphing calculator, it looks something like this. So I see it's not exactly linear, right? I can see it does not have the curve of a quadratic, but I see it kind of does a little something like this, right? Which looks like a cubic model to me. So now I can, in my graphing calculator, I can use this cubic regression. Or in Desmos, here's what I want to type in, right? Except remember that when we're using Desmos for regression, we have to label this 1. We don't have an equal sign here. We're going to have that squiggle. And then we just have to label our x's as 1 as well to tell it which data table to use. I can use the same exact equation. Just make sure that we're in standard form there. And then it will graph our line, or graph our cubic function. And then from there, we can use the function that we're given. And here we're given our A, B, and C, and D, right? We can use that to then write our actual function out and figure out when x equals 22,000 texts per week, then we can figure out the cost. So we can use that function that we came up with in Desmos to help us get there. So let's look back at our learning targets for today. First, we identified some polynomial functions and what makes a polynomial function, and then figured out the degree. Then I graphed polynomial functions using our transformations, our AH and K. Then we looked through the real zeros of the polynomial functions and multiplicity and what that multiplicity means. And remember that if I have that even multiplicity, I touch the x-axis, and if I have odd multiplicity, I go through the x-axis. Then I looked at some graphs. I analyzed and built graphs of polynomial functions. And then I used Desmos to build some cubic models. And remember that when we're building these models from data, we also want to use our graphing calculator or Desmos to help us see which model actually fits best. And you can see that in both of those pretty easily. So now that we've worked through all of these learning targets, go ahead and work on the homework for this section.